All right, I'm back. I've got another topic that I want to talk to you about. I want to go into a little bit more detail, something we introduced when we talked about the scientific method. And we want to talk about hypotheses in a little bit more detail. So you remember that the idea of a hypothesis was central to the scientific method. And so understanding what makes a good scientific hypothesis is important. And it's important for identifying, which hypotheses are scientific and which are not scientific, and what sort of questions are best answered with a scientific hypothesis and things like that. So we just want to talk about the logic of hypotheses a little bit. And one thing that we say about a scientific hypothesis is that a good scientific hypothesis is testable and falsifiable. And so in our earlier example, we talked about a busted flashlight, right? And one hypothesis might be that ghosts fooled with the flashlight, and that's why it doesn't work. Now that could be the correct answer, right? But that is not a scientific answer. There's no way you can test if ghosts fooled with the flashlight. And so although, ghosts might exist and they might be messing with your flashlight, you can't test it, and so it's not a scientific hypothesis. The supernatural and the religious, these are things that are outside the bounds of science. That doesn't mean that they're unimportant, and that doesn't mean that they can't coexist with science. It's just that science has to deal with natural phenomena, and the hypotheses that we use in the scientific method must be testable and falsifiable. Well, supernatural religious explanations, they're not really testable. That's why religion has this thing called faith, because you can't really test it. You just have to have faith. That doesn't mean that that's a bad thing. That doesn't mean these things can't coexist. Now, there are a lot of people who would argue that they can't coexist, and that if you believe in science, you must reject your religion. I am not one of those people. Your brain's big enough to hold both of these things in it, right? You just have to understand the differences between the supernatural and the religious, and the scientific and the not scientific, and how they're applied and when they should be applied to what types of questions. So let's talk about the logic of hypotheses. And so here's a hypothesis, or here's a statement, but it's same kind of idea here. No human lives forever. Is that falsifiable? We want a scientific statement to be falsifiable. Is this statement falsifiable? Well, how would you falsify it? To falsify this statement, you would have to find a human that lived forever. But how could you do that, right? Like, forever is forever. And so you can't really do that. And so the point here is this is a statement that's not falsifiable. So it's not a good scientific statement. It's not useful in science, right? Here's a similar statement. All humans live forever. Now, is that falsifiable? Well, if you think about it, yes. That second statement is falsifiable, right? How would you falsify the second statement? You need to find one human that doesn't live forever. And if you see that, then that falsifies this statement. So just by changing that one word, we've gone from a non-falsifiable statement to a falsifiable one. And it's those subtle twists of logic that are very important for figuring out good hypotheses versus bad hypotheses. We're talking about scientific hypotheses. So a falsifiable statement can be proven wrong. And I know we said we don't like that word prove, but I'm using it in the common vernacular here. It can be shown to be wrong. You can collect data to show that statement is incorrect. So here's, if you're from Southern Illinois like I am, around the Murfreesboro, Carbondale area, you may have been told that a Bigfoot-like creature named the Big Muddy Monster lives in Southern Illinois. Well, is that falsifiable? Can you make an observation to show that is an incorrect statement? Well, you can't, can you? Right? Because if you wanted to falsify this statement, well, we've never seen the big muddy monster. Well, that doesn't really falsify the statement, does it? That's because this statement cannot be falsified. And so it's a very subtle thing, but again, you have to think about the logic of these kind of statements. The statement might be true, but it's not a scientific statement because it's not falsifiable. So here's the same statement again. How could we make this statement falsifiable? Well, you could just change the wording a little bit to say, there is no big muddy monster in Southern Illinois. And so we're talking about the same concept, but now we have a falsifiable statement. How would you falsify the second statement? If you observed the big muddy monster, that would falsify the second statement, right? So that's one of the things that we're trying to hit on here, is that there's a subtle shift in logic and a subtle shift in attitude that kind of makes a scientific statement different from a non-scientific statement. But it's very important to the scientific method. It's very important to what kind of results you end up getting. And so the subtle change in wording between these two statements, I think, shows a subtle shift and change in the philosophy. And so this is something I want you to think about here. The first statement that says that there is a big muddy monster. In that statement, it's sort of like, I'm right, you have to prove me wrong. Whereas the second statement is, I'm assuming I'm wrong, but I'm going to collect evidence to show I'm right. That is kind of the subtle philosophical shift that you get with a scientific hypothesis. And that's something that I think is sometimes underappreciated when we talk about the scientific method. In the scientific method, all scientists assume they're wrong, and everyone else assumes they're wrong. So if I have a hypothesis, of course I think I'm right. Of course I think I have the answer, but I have to assume I'm wrong. And everybody else will assume I'm wrong. Then I have to collect evidence that suggests I'm right. I have to change your mind. Whereas in, like the first statement here, or in other philosophies, people assume they're right, and you have to prove me wrong. It's very much like what we do in the courtroom, okay? And so think about it. In a courtroom, the accused is assumed to be not guilty. And then the court, the prosecutor, the police, they collect evidence to try to change everyone's mind. So the jury has to start by assuming that this person is not guilty. And the prosecutor says, well, what about this evidence? Well, what about this evidence? What about this evidence? And if you collect enough evidence, then you can change people's mind from not guilty to guilty. And so it's the same kind of philosophy that we're using with science here. And so a scientist, everyone assumes the scientist is wrong. And the scientist knows that everyone assumes they're wrong. They got a hypothesis, everyone assumes you're wrong. And then you have to collect evidence that suggests you're right. You say, well, if I'm wrong, what about this? What about this? What about this? And if you collect enough evidence, then people will change their mind. Again, science gives contingent knowledge, not absolute knowledge. So it's the same kind of idea. And so I think it's this type of philosophy is important to the scientific method. This idea that I'm wrong, but I'm going to collect evidence, to show that I'm right. Now, of course, with the big muddy monster, here's your evidence, right? Here's an artist drawing of what somebody says the big muddy monster looked like. So, there's your evidence right there that it exists, right? If that doesn't convince you, well, I don't know what does. Now, this is, again, something I like to bring up because I like to apply this kind of thinking to, like, conspiracy theories. And so, there are a lot of conspiracy theories out there. There's lots of things floating around on the internet. And I've noticed that I think it's this subtle shift in thinking that defines a conspiracy theory. And so when you have a conspiracy theory, the people that promote those, they assume they're right. And then they say, I'm right, you have to prove to me that I'm wrong. And that's different from what scientists do, right? Scientists, assume they're wrong and collect evidence to prove they're right. It's a subtle shift in theory, in philosophy. And so, this is a legit conspiracy theory that's out there. Leaked documents from Democratic politicians have coded messages indicating a secret human trafficking ring is being run out of the back of a pizza restaurant. Now that's just nuts. I'm sorry, but that's just nuts, right? But I'm not making this up. There are people who believe that this is true. And the thing is this is not a falsifiable statement. If you try to falsify a conspiracy theory, then the person who has the theory will just say, well, you're just part of the conspiracy. Like, there's nothing you can do. There's no evidence you can show to convince a person that they're wrong. And that's the difference in philosophy, right? They assume that this theory is right. You have to show me evidence that I'm wrong. But the conspiracy theorist will just reject all your evidence. And so I think that's why it's interesting to contrast that with science. With science, everybody just assumes everyone's wrong until you collect enough evidence that you have to change your mind. And so, that's just something I like to, again, when we're thinking about different ways of knowing, different hypotheses, different things that are out there, your critical thinking skills allow you to recognize these different ways of thinking, and then this could be right. I don't think this is right. I'm going to be very clear. I do not think that this hypothesis about the pizza restaurant is I don't think there's anything correct about it, but some people do. You have to decide, what are you going to believe, and why do you believe that? You think, well, this is, who cares, right? This is just some crazy theory. Hey, somebody went to this pizza restaurant with a gun and shot it up based upon this conspiracy theory. So these things are not harmless. So, I can't tell you what to believe, but again, I can ask you, why do you believe what you believe? And what are you basing that on? And another saying that we like to have here is, don't assume you're correct just because you can't be proven incorrect. And so maybe the reason you can't be proven incorrect is because you have a non-falsifiable hypothesis, a non-scientific hypothesis. So just because I can't come up with evidence to show you that you're wrong, that doesn't mean you're right. So just keep that in mind too. Now, we need to talk about, again, different kinds of hypotheses. We talked about those that are falsifiable, but we also said a scientific hypothesis has to be testable. And so you might say, I might say that I got sick because a student did voodoo on me. Now, is that testable? Like, you might be able to devise some kind of crazy test where you tell them, do the voodoo, no, don't do the voodoo. But really, this is a supernatural phenomenon. You can't test it. Could it be true? It absolutely could be true. There could be voodoo, and they could be doing voodoo that makes me sick. But it's simply not testable, so it's not scientific. So it's not something that we would talk about in a scientific class like this. If a hypothesis is testable, you can make predictions based upon that hypothesis, and then you can realistically observe events based upon that prediction. And so that's an important part. Again, we say when we test hypotheses, what we're really saying is we're making a prediction, and then we're going to make observations to see if that prediction came true. And so, you might have a good hypothesis that makes predictions, but they're not testable. You don't have the right equipment, or it's not realistic to observe those events. That would not be a good scientific hypothesis. But a good scientific hypothesis can make predictions, and then you can collect data, make observations to test that prediction. And so, again, here's an example. The universe was created during the Big Bang. Is that a testable statement? Now, some people would argue it's not testable because, this is supposed to happen, billions of years ago. no one was there, no one can observe it, therefore you can't test it. But it's not true. Just because you can't observe something directly doesn't mean you can't test it. Doesn't mean you can't make predictions from it. If the universe was created during a Big Bang, then we would predict that all galaxies are moving away from each other. And when we look at other galaxies, we see that. All these galaxies are moving away from each other. And so we can test these things. Even though we couldn't observe them directly, we can still make predictions and test those predictions using natural phenomena. All current life evolved from a common ancestor. Again, a common criticism is, well, you can't observe this, so there's no way you could ever test it. And I've got two answers to that. One, we can observe it. There's all kinds of examples of evolution occurring around us that we have observed. And so it's not true that you can't observe evolution. We have observed evolution. But if we want to talk about evolution over hundreds of millions of years or billions of years, some would say, well, there's no way you could make an observation, but there's no way you could test whether that happened a billion years ago. But you can. You can make a prediction. And so you can predict that if all life evolved from a common ancestor, then we should see evidence of those earlier common ancestors. And when you dig in the ground, you find fossils. You find that evidence. You could predict, if all life evolved from a common ancestor, then all life should share characteristics that were inherited from that common ancestor. And you look around and you say, oh yeah, all living things have DNA, and all living things share a lot of characteristics. So that too is testable and is a scientific hypothesis. All current life was placed here by a supernatural being. Is that testable? Is there anything that observation you could make to test whether or not that is true? There really isn't. That doesn't mean it's not true. It just means it's not testable and it's not scientific. You have to decide which explanation makes the most sense to you. But you can see how different sources of knowledge have different answers for the same question. When I die, I'm going to be reincarnated as a catfish. Is that testable? Like, is there any way that we could design a test to see if that's actually true? It'd be awesome. But you can't really test that. It's not scientific. Is it unimportant? What happens after we die? That's a very interesting, important question. And so that's the thing, is no one's saying that these questions are unimportant. They're just not testable, so they're not scientific. So they're not appropriate for a class like this. Diet Coke is better than Diet Pepsi. Is that testable? What does better mean? How are you going to test something like that? That's not really a testable hypothesis. Can we make it testable? You could say that Diet Coke is preferred by more people than Diet Pepsi. Well, then now you have a testable question. So it's you have to think about the logic of these hypotheses. Now, I mentioned this before, that prove is a 4-letter word spelled with 5 letters. We never prove a hypothesis. We can disprove a hypothesis. Again, that's why our hypotheses need to be falsifiable. We need to be able to disprove them. But we can never prove anything. Here's an example. I love all kinds of beer. Can I prove that hypothesis, or can I prove that statement? How would I prove that statement? To prove that statement, I would have to drink all kinds of beer, and I would have to like all of them. But is that possible? So to prove something, you have to test every single incidence of that thing. And that's not possible. That's why you can't prove anything. Now, how would I support this hypothesis? I could try all kinds of beer, and I like all of them. That doesn't prove I like all kinds of beer, but it does support the idea that I like all kinds of beer. Now, how would I disprove this hypothesis? How many beers would I have to dislike? Just one. If I drank one beer, I had one type of beer, and I didn't like it, that's all it takes to disprove this hypothesis. And so again, that's why we focus on that concept of disproving in science. Because, to disprove something is very easy. To prove something is impossible. And so that's why scientific hypotheses need to be falsifiable. So you can disprove them. That's something that can be accomplished. To prove something means you have to test every single instance of that thing, and that's just not possible. So that's why we never say we prove anything. We support or do not support our hypothesis. We fail to reject or we reject our hypothesis. That's the language of the scientist. Now, the last thing I want to talk about having to do with the language of science is this word theory. And so in the common vernacular, most of the time we use theory when we mean hypothesis. And so, I have a theory why the Cardinals are not doing well this year, right? That really is a hypothesis. That's a tentative answer to a well-framed question. And that's fine. That's common vernacular. However, in science, a theory has a very different meaning. A theory is like a hypothesis on steroids. A theory, must be testable, falsifiable, and make predictions. But it also helps to explain things. It helps to tie together different hypotheses. A theory has been well tested and is highly probable. And so often, again, in biology, we talk about the theory of evolution, and, some people will just dismiss it. Well, it's just a theory. Well, when we say theory in science, that has a deeper meaning. And so the theory of evolution ties together many other hypotheses. The theory of evolution has been well tested and is highly probable. So it's not, just like a guess or an educated guess. It's something that has been well established and no one has been able to falsify it. And so it's important that we understand that vocabulary and the difference between the common vernacular and the common use of the word theory. Okay, so that, there we delved into the meaning of hypothesis in a little bit more detail. So again, if you've got any questions, let me know, and I will see you in the next lecture.